Number one, two right triangles must be congruent if. So if I'm trying to prove two triangles congruent, and I know they're both right triangles, that gives me one angle in common already. So I've got one angle, and let's go through each of them. An acute angle in each of the other triangles is congruent. Well, that would just give me two pairs of angles congruent. That's not enough to prove they're congruent. I could prove them similar that way. Let's look at number two. The lengths of the hypotenuses are equal, so something like that. That would only be one angle on one side. Remember, I would need to prove three pairs of things are congruent for congruent triangles. And number three says the corresponding legs are congruent, so something like that and that. Remember, the legs of a right triangle are the ones that form the right angle. And in this case, if I mark it up like this, this is a side angle side proof that would prove these two triangles congruent. So by side angle side, that would be enough information. Number two, given triangle ABC with the measure of angle B is equal to 62 degrees, with side AC extended to point D out here. Which value of x would make it so that AB is congruent to CB? Now that would mean that this triangle ABC is isosceles, which would mean those base angles would need to be congruent. So if those base angles were congruent, I could figure out what they are by subtracting 62 from 180 and dividing that 118 by 2. Because remember, all of the interior angles of a triangle should sum to 180 degrees, so if one of them is 62 and the other two are equal, the other two must be 59. Now, this angle x out there, this angle x right here, which is an exterior angle, should be supplementary to that 59 degrees. This is the picture here. If they add up to a straight line, they together should sum to 180 degrees. So if I take 180 and subtract away 59, I'll find that the supplement to that angle is 121 degrees. Number three, line segment EA is the perpendicular bisector, so I know it makes right angles, and it breaks ZT into two congruent segments, of ZT and ZE and TE are drawn. Which conclusion cannot be proven? Well, if you notice there are two triangles on either side here, and they both share this side EA, triangle ZEA can be congruent to triangle TEA by side angle side. So if I know the triangles are congruent, I know all of the corresponding parts of these two triangles are also congruent. So number one says segment EA bisects angle ZET. So the question is, would I be able to prove those two angles up there congruent so that E is getting cut equally in half? And the answer is yes, because those are corresponding parts of these two triangles here. So that would be like a CP-CTC argument. Now, in order to prove that EZT is equilateral, remember that would mean that there are three congruent sides. Now, I can prove that ZE is congruent to ET by CP-CTC, but I wouldn't necessarily be able to say that ZT is also the same length as those other sides. So I could prove it's isosceles, but not that it's equilateral. Now let's go through the other ones just to make sure. EA is the median of triangle EZT. Remember, a median goes to a midpoint, and if I know the segment's already a bisector, then it must be the case that A is the midpoint there. And angle Z congruent to angle T, well again I can make a CP-CTC argument to say that those two angles are congruent. Number four, given triangle ABE, so triangle ABE, I'm just redrawing it over here, and triangle CBD, I'm going to redraw it with the same orientation, CBD, below with segment DB congruent to BE, and mark that here like that. Which statement is needed to prove that the two triangles are congruent using only side angle side? Well, notice both of these triangles overlap at angle B, so angle B would be congruent to angle B in these two triangles by the reflexive property. So if I wanted to prove side angle side here, I would really just need some information to say that AB and CB are the same length. The problem is none of my answer choices say that. Since I know I'm looking for a side, I could rule out the angles here. But notice segment AE congruent to CD. If I had that information, that would actually be side angle angle because the angle's not in between the sides. So just by process of elimination, I know that can't be it. But let's look at why answer 3 is the correct choice. If I go back to my original picture, and if I say that AD and EC are congruent, then I can say by the addition property that AD plus DB is congruent to EC plus BE, which in turn would just prove that segment AB, up there, is the exact same length as segment CB, which is right there. And that would give me the side angle side I need. So that's making an argument with the addition property. Number 5. In the diagram below, lines L, M, N, and P intersect line R. Which statement is true? So if I'm looking for a pair of parallel lines, there's really two things you want to be looking for. Either you want to look for congruent alternate interior angles, where your angles are between your parallel lines but on opposite sides of the transversal, or some sort of pair of congruent corresponding angles, where in the same place relative to each other. Now, in this case, if this angle is 112, if I subtract from 180, the supplement to that would be 68 degrees right here. And I notice that that 68 degrees also appears in line P. Now, if I pretend those other lines aren't there for a moment, notice that I'll call this angle 1 here and angle 2, that angle 1 and angle 2 are congruent corresponding angles. That's because if I take one of them and translate it onto the other, they would lie perfectly on top of each other. So showing that we have congruent corresponding angles would be enough to justify that line L is parallel to line P. Now, we could also make an argument with congruent alternate interior angles. I know that this angle right here is 68 degrees, and by vertical angles, this angle is also 68 degrees. So if I trace out the Z there, you can make an argument that L is parallel to P because they form congruent alternate interior angles as well. Number 6, Kelly is completing a proof based on the figure below. She was given that angle A was congruent to angle EDF right there. Remember that middle letter is the vertex. And she already proved that segment AB, right here, is congruent to segment DE. Which pair of corresponding parts and triangle congruency methods would not prove the triangles are congruent? Well, if I had, let me just redraw these so that they're in the same orientation. A, C, B, and I notice that A and D are congruent angles, so that's where D should go. E should match up with B, and F should match up with C. So I'll put F up here and E right down there. I already know this, and I already know that. So if I know AC is congruent to DF, that would be a side angle side proof, so that's okay. But if instead I knew BC was congruent to EF, again, this is a side-side angle argument. The angle is not in between your sides here, so that would not work as a way to prove these triangles congruent. If you go through the rest of them, if you know that angle C and angle F are congruent, that would be angle, angle, side, and answer choice 4 would indeed get you angle, side, angle. Number 11. Given isosceles triangle ABC with sides CA and CB congruent, and CD is the median to AB, prove the triangle ACD is congruent to triangle BCD. Well, I wrote down my givens, and I'm just going to walk you through what one thought process for this could be. If you recognize the word median, remember that goes to the midpoint of the opposite side. So the first thing I said here was that D is a midpoint of AB because a median goes to a midpoint. And if I recognize that D is a midpoint, I know a midpoint divides a segment into two congruent parts. So I can make an argument that AD and DB are congruent because a midpoint divides a segment into two congruent segments. Now I've got two sides. Really all I need is an angle or a side. This is an isosceles triangle, so I could say congruent base angles, or it might be easier to recognize that both of those triangles share a side in common CD. That would be a reflexive property. So by side, 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 these two triangles are congruent. That could be one way to look at this proof. Again, for most of these, there will be lots of different ways to look at them. For number 12, given that AF is congruent to CD, that BC is parallel to FE, and that angle A is congruent to angle D, prove these two triangles congruent. Well, I noticed that both of these triangles share FC, and even though that isn't a full side length, I can still say that FC is congruent to itself by the reflexive property. The reason I say that is because if I take AF and I add FC to it, that would get me the whole side length AC. And if I take CD and I add FC to it, that would give me the whole side length DF. So the argument we're going to make here is that if we take AF plus FC, that should be the same as CD plus FC, because those parts are congruent, and we've already shown that FC and FC are the same. So if I sum equals, the sum of them should also be equal. So AC is congruent to FD by the addition property there. Now I still need another angle, and notice that we haven't used the parallel part yet. So I notice that angle BCA right there and angle EFD are congruent alternate interior angles if we trace out the Z there. So the next statement I made here was that those two angles I've marked are congruent because parallel lines form congruent alternate interior angles. And then that would be enough to prove the triangles are congruent by angle side angle. I've got two angles, and I've proven that the side between my angles is congruent. For number 13, given that angle 1 is congruent to angle 2, and segment AC bisects segment BD, prove triangle ABC congruent to triangle EDC. Well, remember a segment bisector divides a segment into two congruent parts. So that was the first thing I said for this proof, that BC and CD are congruent. Then I labeled this as angle 3, and this is angle 4, because angle 2 and angle 1 actually aren't angles of my triangle. So I could use them to prove an angle in my two triangles are congruent. In this case, I said that angle 1 and angle 3 are supplementary, and angle 2 and angle 4 are supplementary, because adjacent angles on a line are supplementary. They should add to 180. Now, if I know that 1 and 3 are the same, like let's just say for argument's sake they're both 120, I would know the supplement to both of them would be 60 degrees. So with that logic that they both have supplementary pairs, I could say that angle 3 is congruent to angle 4 because supplements to congruent angles are also congruent. Now I either need another side or another angle, because all I've got is an angle and a side at this moment. But don't forget that there's a pair of vertical angles in there, angle ACB and angle DCE. So that was the last thing I said there, that angle ACB is congruent to angle DCE by vertical angles, and then by angle side angle again, these two triangles are congruent. For number 14, there are many ways to go about this. You could know that opposite sides of a parallelogram are congruent and parallel, whatever helps you here. But we're looking to prove triangle ADD is congruent to triangle CEB. Well, I know that opposite sides of a parallelogram are congruent, so I can mark those congruent. I believe that was the first thing I said here. In a parallelogram, opposite sides are congruent. And I also know that the diagonals of a parallelogram bisect each other, and a segment bisected divides a segment into two congruent parts. So my next statement was that AE and EC are congruent, and DE and EB are congruent, because in a parallelogram, the diagonals bisect each other. So for me, this was a quick side-side-side proof. You could have used angle-side-angle if you maybe use those vertical angles and those congruent alternate interior angles, but it's up to you. Number 15. Given ABCD is a rectangle, and M is the midpoint of AB, prove that DM is congruent to CM. Now, if I'm trying to prove two parts of two triangles are congruent, that's going to first have me prove that the triangles are congruent, and then make a CP-CTC argument after that. So the first thing I recognize is, I know the definition of a midpoint is that it divides a segment into two congruent parts. So segment MB is congruent to segment AB. But I also know that this is a rectangle, so the opposite sides of a rectangle are congruent. So segment DA is congruent to segment CB, because in a rectangle opposite sides are congruent. Now, I need another side or another angle to prove the triangle DAM is congruent to triangle CBM. And the reason I'm going for those triangles is because DM and CM are side lengths of those triangles that would be proved congruent by CP-CTC. Remember, a rectangle has four congruent right angles. That's one of the properties of a rectangle. So angle A is congruent to angle B because a rectangle has four congruent right angles. And triangle DAM is congruent to triangle CBM by side angle side. Now, if I have all that information available to me, I can then make a CP-CTC argument. Let me just move this out of the way. That these two triangles are congruent, therefore their corresponding parts are congruent. Let me just get this away for a moment. So that piece and that piece are the same. So anytime I'm asked to prove that two angles or two sides are the same, I want to first prove triangles congruent and then state that the corresponding parts of congruent triangles are also congruent. In the diagram below, lines P and S are cut by transversals. The angles are marked as shown. Explain why P and S must be parallel. Again, if I'm proving lines are parallel, I want to show either congruent alternate interior angles or congruent corresponding angles. Either would work in this case, but the idea is that this angle right here, together with the 63 and the 74, should sum to 180 degrees, because all of those angles lie on a straight line. So in order for that to happen, that angle needs to be 43 degrees. So I labeled that as angle 1, and I said that needs to be 43 degrees because adjacent angles on a line should sum to 180 degrees. And if that's the case, that's really all you would need to prove these lines parallel. If that angle down there is 43 and that up there is 43, I know the lines are parallel because congruent alternate interior angles make parallel lines. So we could have also used this inside triangle to make an argument that all those angles should sum to 180. So if you subtract from 180, that angle is 63 degrees, and then you could make a congruent corresponding angles argument, but both would be acceptable. And for this last one, given that TD is perpendicular to RS, remember that means that they intersect at a right angle, and that ME is perpendicular to SE, or SR, and again that gives me a right angle. RD is congruent to SE, and TD is congruent to EM. I want to prove that segment RM is parallel to segment ST. In order to do that, I would need to show that I've got a pair of congruent alternate interior angles here. And in order to prove those angles congruent, I would first need to prove that the triangles are congruent and then use a CP-CTC argument. So I marked some right angles there, but I didn't talk about them. So the first thing that we might say here is that angle TDE is congruent to angle REM. Those are the right angles I marked, because perpendicular lines form congruent right angles. Now they also gave me that these little pieces RD and SE are congruent. Those are only parts of side lengths of triangles, but if I add them both to segment DE, I would get full side lengths. So because these triangles are overlapping, this is going to be another addition argument, that I can say that segment DE is congruent to segment DE by the reflexive property, and then if I take RD and add DE to it, that should be the same length as ES plus DE, because the individual parts are the same, which would show that segments RE and DS are congruent. So that gives me another side. And that would give me a side angle side proof to prove the triangle REM and angle TDS are congruent. And that's what my goal was in the first one, because if those triangles are congruent, I could say that this angle here and that angle there are congruent. You could name them as ERM, or I just labeled it as 1, by CPCTC. So the triangles are congruent, therefore the corresponding parts would be congruent. And if those angles in particular are the same, those are congruent alternate interior angles. And I know that congruent alternate interior angles make parallel lines. So my last statement should always be what I'm trying to prove. TS is parallel to RM because congruent alternate interior angles make the lines parallel. So anytime I'm looking for parallel lines, it's very similar to a triangle proof, only I make a CPCTC argument to say either congruent alternate interior angles or congruent corresponding, and use that to justify that my lines are parallel.